Hello, everyone. The topic of this online class is computational chemistry. Computational chemistry is a branch of chemistry that uses computer simulation to assist in solving complex chemical problems. It exploits methods of theoretical chemistry, incorporated into efficient computer programs, to calculate the structures, the interactions, and the properties of molecules. Section 1. The Nobel Prize in Chemistry. I will briefly introduce the Nobel Prize winners in chemistry in the field of computational chemistry. 1. Computational chemistry, Gaussian and Gauss view. The Nobel Prize in Chemistry 1998 was divided equally between Walter Kahn, for his development of the density functional theory, and John Pople, for his development of computational methods in quantum chemistry. Walter Kahn and John Pople are the two most prominent figures in the process of an enormous theoretical and computational development. Walter Kahn's theoretical work has formed the basis for simplifying the mathematics in descriptions of the bonding of atoms, a prerequisite for many of today's calculations. He showed that it is not necessary to consider the motion of each individual electron. It suffices to know the average number of electrons located at any one point in space. This has led to a computationally simpler method, the density functional theory. The simplicity of the method makes it possible to study very large molecules. John Pople developed the entire quantum chemical methodology, now used in various branches of chemistry. Pople made his computational techniques easily accessible to researchers by designing the Gaussian computer program. The first version was published in 1970. The program has since been developed and is now used by thousands of chemists in universities and commercial companies the world over. 2. Computational chemistry, MD, molecular dynamics, simulation. The Nobel Prize in Chemistry 2013 was awarded jointly to Martin Karplus, Michael Levitt, and Ari Warshel for the development of multiscale models for complex chemical systems. Chemists used to create models of molecules using plastic balls and sticks. Today, the modeling is carried out in computers. In the 1970s, Martin Karplus, Michael Levitt, and Ari Warshel laid the foundation for the powerful programs that are used to understand and predict chemical processes. The work of Karplus, Levitt, and Warshel is groundbreaking in that they managed to make Newton's classical physics work side by side with the fundamentally different quantum physics. MD simulation is a computer simulation method for analyzing the physical movements of atoms and molecules. The atoms and molecules are allowed to interact for a fixed period of time, giving a view of the dynamic evolution of the system. In the most common version, the trajectories of atoms and molecules are determined by numerically solving Newton's equations of motion for a system of interacting particles, where forces between the particles and their potential energies are often calculated using interatomic potentials or molecular mechanics force fields. The MD simulation is applied mostly in chemical physics, material science, and biophysics. These days, computer models mirroring real life have become crucial for most advances made in chemistry. Section 2. Gaussian and Gauss view. Before learning the basic usage of Gaussian and Gauss view programs, I will briefly describe the features of both programs. Gaussian is the electronic structure program used by chemists, chemical engineers, biochemists, physicists, and other scientists worldwide. Gaussian provides a wide-ranging suite of the most advanced modeling capabilities available. You can use it to investigate the real-world chemical problems that interest you, in all of their complexity, even on modest computer hardware. A general-purpose computational chemistry software package, initially released in 1970 by John Pople and his research group at Carnegie Mellon University as Gaussian 70. It has been continuously updated since then. Originally available through the Quantum Chemistry Program Exchange, it was later licensed out of Carnegie Mellon University, and since 1987 has been developed and licensed by Gaussian, Incorporated. Starting from the fundamental laws of quantum mechanics, Gaussian predicts the energies, molecular structures, vibrational frequencies, and molecular properties of compounds and reactions in a wide variety of chemical environments. Gaussian can be applied to both stable species and compounds, which are difficult or impossible to observe experimentally, whether due to their nature, for example, toxicity, combustibility, radioactivity, or their inherent fleeting nature, for example, short-lived intermediates and transition structures. With Gaussian, you can thoroughly investigate the chemical problems that interest you. For example, not only can you minimize molecular structures rapidly and reliably, you can also predict the structures of transition states and verify that the predicted stationary points are in fact minima or transition structure, as appropriate. You can go on to compute the reaction path by following the intrinsic reaction coordinate, IRC, and determine which reactants and products are connected by a given transition structure. Once you have a complete picture of the potential energy surface, reaction energies, and barriers can be accurately predicted. You can also predict a wide variety of chemical properties. Gauss View is the most advanced and powerful graphical interface available for Gaussian. With Gauss View, you can build or import the molecular structures that interest you, set up, launch, monitor, and control Gaussian calculations, and view the predicted results graphically, all without ever leaving the application. Gauss View includes many new features designed to make working with large systems of chemical interest convenient and straightforward. It also provides full support for all of the new modeling methods and capabilities available in Gaussian. Molecular mechanics is one aspect of molecular modeling, as it involves the use of classical mechanics or Newtonian mechanics to describe the physical basis behind the models. Semi-empirical methods are simplified versions of Hartree-Fock theory, using empirical corrections, which are from experimental data, in order to improve performance. Ab initio quantum chemistry methods attempt to solve the electronic Schrödinger equation, given the positions of the nuclei and the number of electrons, in order to yield useful information, such as electron densities, energies and other properties of the system. A basis set in theoretical and computational chemistry is a set of functions that is used to represent the electronic wave function in the wave function, or density functional theory, in order to turn the partial differential equations of the model into algebraic equations suitable for efficient implementation on a computer. Density functional theory, DFT, is a computational quantum mechanical modeling method used in physics, chemistry, and material science to investigate the electronic structure or nuclear structure, principally the ground state, of many body systems, in particular atoms, molecules, and the condensed phases. Using this theory, the properties of a many-electron system can be determined by using functionals. In this lecture, we will use 6-31G as the basis set and B3OYP in density functional theory as the method. Through this lecture, we check the optimized structure of molecules and calculate the spectrum of vibrational motion. In addition, the structure of the hybrid orbital will be displayed, and the chemical reaction process will be confirmed by calculating the intermediates of the chemical reaction.